we'll go to review the D0 brane holography. Then we'll come back to the matrix bootstrap. Okay, so that's the plan for today. Okay, so one more thing about the matrix bootstrap, or the bootstrap in general, before we go on to D0 branes, which is the generalization to finite temperature. So yesterday I talked about bootstrapping at finite energy, in particular the ground state, but there's a nice generalization of these ideas to bootstrap the canonical ensemble. Okay, so what is the idea? So yesterday we discussed the left-hand side of this equation, right? So we said that in the ground state, this quantity is always positive, right? That was just a statement that if you perturb the ground state by some operator, the energy has to go up, right? So this was interpreted as some delta E, basically. Right? And there's a nice generalization of this inequality due to Rocky and Sewell. So it's some old work which says that for a finite temperature ensemble, you actually have this full inequality. So when beta is going to infinity, that's what we had last time. When beta is finite, we have a new term on the right-hand side. Okay, and very roughly, you should think of this as like the change in free energy being positive, right? So if you like, this log looks a little bit like an entropy. So you can roughly think about this as like a T delta S term. I put this in quotes because I actually don't quite know how to make this precise. Okay, so this is an inequality. And for example, you can check it if you like. So I haven't given any exercises in this mini course, but a simple exercise is to check this inequality for the harmonic oscillator. Okay, so you choose O and O dagger to be just creation and annihilation operators, and just check that this inequality is true. Okay, and what you will find is that it's actually precisely saturated in the thermal case, right? So this inequality is not symmetric under O goes to O dagger. So by choosing O to be a creation operator or annihilation operator, you actually get two inequalities. And for both of them to be true, you actually need equality. And you will see that this inequality actually implies the full statistics of the thermal state for the harmonic oscillator. So that's kind of an instructive exercise. Okay, so this is some inequality. And, well, it can be used to do bootstrap. So for example, Fauzi-Skelet pointed out that one can bootstrap, let's say, simple correlators in a spin system using this inequality. And the idea is that if the inequality is true for all possible operators O, okay, then this is somehow equivalent to imposing the KMS condition. So that's not totally obvious, right? Because the KMS condition is a condition on two-point functions, right? It says that the two-point function is periodic in Euclidean time. And this is a condition on just one-point functions, quote unquote, right? So these operators are all evaluated, let's say, at the same time. But of course, that's a little bit of a joke because if the operators are arbitrarily complicated, you can essentially get a black hole, and F is just 1 minus this to the D minus 3, right? So the question is, what factor of D should I put in here? Well, you say, well, maybe I should put D equals 11 because I'm looking at an 11D Schwarzschild black hole. Okay, that's one idea, but there's some two immediate objections that you might have, okay? So first of all, if I put D equals 11 here, I'm not going to get to a solution which is homogeneous in any small circle in which I can do the reduction, right? And a second objection is I'm looking for a solution which is charged, right, in the 10D picture, right? So I should look for a solution which carries momentum, and the Schwarzschild black hole is just sitting still, right? So these are two objections to putting D equals 11. So the idea is to simply put, to modify the solution in an extremely simple way, which is to put D equals 10 here, and then add one extra direction, dy squared. So now this is an 11-dimensional solution, right? Oh, sorry. The plus dy squared goes in the metric. Okay. Right, so this is the black string solution in 11 dimensions. So this solves objection 1, right, which is now we have a compact direction. So dy could be a compact direction. And the solution is homogeneous, of course, in this y direction, right? And now to address the second objection, we simply boost the solution, okay? So we simply do some Lorentz transformation, let's say cosh alpha, sinh alpha. So we just do a boost in the y direction. So when you boost the solution, of course, then you give it momentum in that in the y direction. And when we do dimensional reduction, that will be interpreted as charge. Okay. So now you can check as an exercise, take this solution, do the boost that I just said, and then do the dimensional reduction, and you will find the solution. Right. So recall that the 11D solution, the relation between 11D metric and the 10D fields. So this is a 10D metric, right? In order to embed this, we need some factors like, and then we have some A mu. Well, yeah. So we should just, okay. Basically, you should think of this, right, as the 11, you put the 10-dimensional solution here, right? And then you have the dilaton, which roughly speaking is this component here, although usually we write it in a convention where it both multiplies this, and then we have A mu here, right? So this is just the standard relation between 11D M-theory and 10-dimensional solution, right? So once you do the dimensional reduction, you will find exactly the solution with these factors of alpha, right? So these trig factors come from this boost. Okay, so that's just a simple way of getting this solution using some solution that you already know, which is the Schwarzschild solution. Okay, so well, one minor comment is that this is a black string, right? So it's a black string in 11 dimensions, and there's a Gregory-Laflamme's instability that we should worry about. Okay, but let's discuss that. Let's postpone the discussion of that to a little bit later. Okay, so this is, now we found a solution to type 2a supergravity, let's say, that has asymptotically flat space, right? So this is an asymptotically flat solution, and as you're familiar with, in order to follow the ADS-CFT logic, we should try to take a decoupling limit. Okay, so let's briefly review that logic, okay? So the idea is we can consider some energy spectrum of this theory, of the full string theory, right? So we're considering the energy spectrum, let's say, of the full type 2a string theory in the presence of n d0 branes, right? So the spectrum starts at n, right? The BPS bound tells you that all the energies start at n and are positive, right? There can be there's nothing in here, and there's some spectrum here, right? And the idea is that we're going to take the limit g string goes to 0, zooming in on these energies. So we're going to, we're going to consider energies, so delta E. So delta E, let's say, is the energy minus n. We're going to consider energies in string units which scale like g string to the 1/3 power. Okay? So let's now consider what happens from two different points of view. Okay? So on the one hand, we have the closed string point of view. So that's described by this metric, right? And we can try to analyze what kind of excitations would survive in this limit, right? And so one kind of excitation is you could consider a particle living in this geometry, right? And if this particle is in the near horizon region, it will have an energy that actually goes like g string to the 1/3. So more precisely, if the particle has a location r over L string that goes like g string to the 1/3, then you can check that the redshift factor in this metric will lead to an energy which goes like what I said. Okay? Another thing you can do is you can make the temperature of this black hole extremely low, right? So this black hole has some energy itself, right? And if the temperature of the black hole is very low, it can go like g string to the 1/3. Okay? So so what we conclude is basically if we zoom in on this near horizon region, so we consider all excitations which live inside this tiny region here. So it includes the black hole interior and also a tiny thin strip near the horizon. The amount that it, it's basically just this formula. And we also consider temperatures, like, so the temperatures related to the horizon scale are not. So if we like, we can think of either excitations that are at some radius r, or we can just think of this formula as a formula for the radius of the black hole itself. Both of them should go like g string to the 1/3. We will survive this decoupling limit. Okay? So that's the closed string point of view. There's a second point of view, of course, which is the open string point of view, in which case we should think about the d0 brane theory itself, right? So the de-zero brane theory itself is described by some Hamiltonian, which has this commutator square term that we mentioned last time. And it also has fermions, right? So it has 16 supersymmetries. We will discuss more precisely the form of the Hamiltonian shortly. But the main point is that this is the low energy effective action, right? The low energy theory. In principle, there are also higher derivatives, and those are suppressed by alpha prime, right? But here we're considering energies in string units, which are very tiny, right? So we can drop all of those higher derivatives, okay? So this conversion, when you remember that G squared Yang-Mills is basically just G string in units. So G squared Yang-Mills in 0 + 1 dimensions has units of, has some mass units, right? So it has units, and in particular it has mass dimension 3, right? So this formula tells you that what we're essentially doing when we're scaling the energy in this way is that we're considering energies in this theory that are finite, but they're low compared to any higher derivative corrections that we might consider. So you can put any energy in this theory that's fixed in the Yang-Mills coupling, but it's small compared to any like alpha prime corrections, right? Okay, so then the standard decoupling on logic equates the two theories, right? So we're supposed to equate the de-zero brane theory with the near horizon region here. Okay, slightly more precisely, we can say that the argument that I gave identifies two kinds of excitations. So there are excitations that live inside, let's say, this near horizon region, and there are also far excitations, right? You could just have some very low energy mode that lives in the flat space region. That would also be some excitation that's allowed in the decoupling limit. But in both cases, those excitations are the same, right? So from the point of view of the closed strings, this is just some very low energy, let's say, massless mode that lives in the flat space region. And also in this theory, we should also think of this as the tensor product, let's say, of the de-zero brane theory tensored with the flat space theory. Okay, so we'd also have excitations in the flat space region. And since the flat space region is basically the same in both descriptions, we sort of cancel them from both sides. So here we think of this as h of the near horizon. We don't exactly know what this is in quantum gravity, of course, but this is sort of in quotes, right? Tensored with the h of the flat space theory. And in this case, the flat space theory is actually weakly coupled string theory. So that's a difference between the logic for decoupling in the n = 4 super Yang-Mills case and the de-zero brane case. In the de-zero brane case, you need to take the G string goes to 0 limit in the flat space region. So in the flat space region, you just have some free theory, basically, that is consists of the massless modes of string theory. It's not very interesting. We think we understand it, so we can cancel it from both sides. Okay, so the duality is, of course, that these two things are the same. Okay, so now what I've done here is I've just written the same metric, but I've taken the decoupling limit. So in particular, because we're supposed to consider the near horizon region, it's convenient to define some coordinate rho, which is fixed as we take G string goes to 0. And this coordinate is basically just R0 over LS G string to the 1/3, okay? So defining these coordinates, we now get this metric. Basically, the only thing we do is we drop the 1. So it's very similar to the n = 4 case. And we get this metric, and we would like to now analyze some of the properties of this metric. Okay. Sorry, R. Yes, thank you. Yeah. There's also ρ0, which is the same formula with r0. Okay. So let's now stare at this metric for a little bit. Okay, so first thing to notice about this metric, just in the rho coordinates, is that there's this factor of rho to the -3/2 d omega h squared, right? That's kind of a funny factor if you think about it. That says that the sphere, so this is in string frame, the sphere is shrinking as you go to large rho, right? So if you think of this as like, it's not really like a standard black hole, right, where the sphere grows, right? Here the sphere shrinks. And in particular, it shrinks to 0 size, right? So this already tells you that there's something funny. So in particular, if you calculate the invariant curvature, the curvature is going to get very large. It's going to get very large just because the sphere is shrinking. That's one reason why it's getting very large, right? So if we like, we can draw a Penrose diagram of this metric. So let's try to be a little bit more precise. So first, let's do a change of coordinates from rho to z. So z is just equal to rho to the minus 2/5. Okay, it's just some transformation. But now it looks like something that we're more familiar with. Okay, after doing this trivial change of coordinates, it looks like a factor which looks like ADS times an S8, right? So this looks like, quote, ADS2 times an S8, right? This factor of f looks like the emblackening factor for a black brain in ADS, okay? So, yeah. ADS in d dimensions, you would have a black brain which has exactly this form, okay? So, thank you. Yes, thank you. Okay, so we can draw the Penrose diagram by just ignoring this factor, of course, and it just looks like the same diagram that we would draw in ADS, right? So for an ADS black brain. So this region now has become this region, okay? We've lost the flat space region. We just have the near horizon region, which is depicted in this Penrose diagram. The only difference is perhaps we should draw a squiggly line here and here. Right? So why do we draw that? It's because the geometry is becoming very singular as rho goes to infinity. Right? So as rho goes to infinity, the curvature is becoming large. And intuitively, this is not very unreasonable. This is kind of reasonable. So why is that reasonable? Well, you just have to remember this fact, basically. Okay, so G squared Yang-Mills has some units, right? So it's not the conformal field theory, and in particular, it's a relevant deformation in dimensions less than 3, right? So it's a relevant deformation. That means in the UV, the theory is basically a free theory, right? So a free theory should not have a nice gravity dual. And indeed, we see that the gravity dual is becoming singular in the UV. If we look at the dilaton, we actually have a similar kind of thing, right? So the dilaton is like the effective coupling. So it's true that GS in the decoupling limit is 0 in the flat space region, but the effective dilaton is this e to the minus 2 phi thing, and that's actually being held fixed in the decoupling limit. So the dilaton is actually fixed, and if you plot it, it just grows, right? It grows towards the center of this bulk. So that, again, is kind of reasonable if you think of this as some sort of coupling. From RG, right, we think of the coupling for a relevant theory as becoming stronger in the infrared, and that's reflected in this geometry as well. Okay, so it looks a bit like ADS, but of course the dilaton and the gauge field breaks the ADS isometries, and also this factor of z to the 3/5 is not what you expect from ADS. Okay, so nevertheless, this solution has an interesting scaling symmetry. Okay, so this scaling symmetry was noted in the past, and it was highlighted again more recently in this paper by Biggs and Malasena. And the scaling symmetry is just a rescaling of z and t, right? So if you rescale z and t, this solution gets rescaled, right? So in particular, that changes the value of z naught, right? And the action, the type 2a action, is not invariant under this rescaling. So it is not the symmetry of the theory in a conventional sense, right? A symmetry leaves the action unchanged. But here there's something that's very close to a symmetry in the sense that a rescaling of this solution only leads to an action that gets multiplied by some factor, right? So I basically goes to I, gamma to some power, some power, and that power is related to the thermodynamics of the model. Right, so the action changes very simply. If you ask me later, I can also explain why this same symmetry leads to power law correlators in the solution. Okay, so more precisely, if you consider supergravity modes in this background. So we're not discussing massive modes right now. We're just discussing massless modes. The massless modes correspond to operators such as trace z to the k in the boundary theory, right? Where z is x plus I, y, where these are two of the scalar matrices. So we could consider a correlator like this. Let's say at very low temperatures. So at very low temperatures, we could consider a correlator like this. And the claim is that these correlators look like conformal correlators. So they go like 1 over tau to some particular, with some particular scaling dimension. Okay? And this is closely related to the scaling symmetry that I just mentioned. So even though this theory does not have a conformal symmetry, there's an emergent scaling symmetry in the low energy type 2a limit. Okay? So let me be a little bit more precise now. So what approximations have we made? We're assuming that we have a type 2a solution, right? In pure supergravity solution. But as I said, this is a high curvature solution in the UV, right? So we should worry about the validity of this approximation. And indeed, the validity depends on what the value of R naught is, or rho naught. Okay? So for rho naught of order 1, okay, rho naught of order 1, this horizon is not very parametrically suppressed compared to the region of high curvature, right? So if you like a different picture, we can attempt to draw the this solution. So here I'm just depicting the size of the sphere, the d omega 8. So there was a flat space region, and now we've taken the decoupling limit, so we basically forget about the flat space region, and we just focus on the size of the sphere as a function of the radius, right? So normally the sphere would shrink, but here the sphere is actually growing as we go into the bulk, and it's shrinking as we go towards the UV. And there's a horizon, right? So in the Euclidean solution, there's a horizon, and where the horizon is determines the size of the sphere, right? So if the horizon, if we're at very high temperatures, okay, this horizon would be like right here, and the curvature scale of the sphere would be of order of the string scale, and we would not be able to trust the solution. But if we take temperatures much smaller than 1 in Tuft units, okay, temperatures much smaller than 1 in Tuft units, there's a nice parametric separation between the stringy region and the location of the horizon. Okay, so this means that we can actually reliably trust the computation of the thermodynamics using this black hole solution at very low temperatures. Okay, so there's 2 low temperatures. Don't confuse them. First, there's the low temperature limit that we took for decoupling. Okay, that says that we focus on low temperatures with respect to the flat space. Okay, now there's a second low temperature limit. So the decoupling logic applies for any rho naught. Okay, rho naught could be in Tuft units could be 1, it could be small, it could be whatever. Okay, the only thing that was important was that R was very small in string units. Okay, but rho is fixed. Now, if the temperature is further much smaller than the Tuft scale, then we can trust the type 2a solution. Okay, so to say it in a little bit better in formulas, we can summarize the situation as follows. So we can study concretely, let's say, the thermodynamics of the black hole. That's perhaps the simplest thing. So if we study the energy of the black hole as a function of temperature, we will get something like this. So there will be temperature to the 9/5 power. And here I'm writing temperature in units. So temperature has some units. I'm using Tuft units. So I'm using units. So lambda is g squared n, okay? And as I've emphasized already, this Tuft parameter has some units. So it has mass dimension 3, and therefore we can make any temperature by, so whenever I write the formula with the wrong units, you should combine it with the appropriate powers of lambda to make it dimensionless. Okay, so this formula uses this convention, and this coefficient here is predicted just from the, predicted from area over 4g Newton, right? Where we evaluate the area in this type 2a solution. Okay, then in addition to this, we would have other corrections. So we could have a correction like c to the 23 over fifths, right? We could have further corrections. So let's discuss that in 1 second. We could also have 1 over n squared corrections. Okay, so there are also 1 over n squared corrections. And for each order in 1 over n squared, there'll be a bunch of different powers that appear, right? So you should contrast this a little bit with the situation in n equals 4 super Yang-Mills, where there's basically, for a planar black hole, right, the only thing that we know, well, conformal symmetry fixes the temperature dependence, and then there's just the function of the coupling that we want to know, right? This is the famous 3/4, the interpolating function that goes between 1 and 3/4, from weak coupling to strong coupling. Here, the temperature dependence is not fixed. The only thing that this scaling exponent, 9/5, was fixed by a scaling symmetry, but that scaling symmetry only holds in the supergravity regime. Okay? Once we include string corrections and so forth, there can be all sorts of other powers of temperature that appear, and there's different powers that can appear at different powers of 1 over n squared. Yes?
Don't you have an issue here whether you're computing the energy in the string frame metric or in the Einstein frame metric?
I don't think there's an issue. So I think we're defining it by the ADM mass. So if you like, yeah, you can also think of this as the energy as measured essentially with respect to flat space. So that makes it unambiguous.
Well, I need to think about it. Okay, thanks.
Since Jorge asked, let me ask a similar question. So you mentioned a few times that these Penrose diagrams and so on are in the string frame. Would the discussion change in the Einstein frame, or it's more or less the same?
Yeah, so the Penrose diagram won't change whether we're in string frame or Einstein frame.
Sure.
But yes, for example, these factors will change. I mean, they will change by the factor of the dilaton, which is some z to some power. So in particular, the sphere will actually not have this funny feature in Einstein frame. So the sphere actually does grow at large R in Einstein frame. That's the statement that the entropy of the black hole gets bigger as we increase the temperature.
Okay.
Yeah.
And the Einstein frame is the best one, right?
Well, it depends. Okay. Well.
It's the physical one, no? Should I follow the Einstein one, right?
Well, okay. We have to discuss this in a little bit more detail. So, so for example, the massive stringy modes, they follow geodesics in the string frame. So the massive string states, they follow geodesics in the string frame. You can ask about the massless modes, and well, I can discuss that. Well, okay. Let me tell you what happens to the massless modes. If you just consider a massless mode coming from this action, so for example, you could consider basically e to the minus 2 phi times a small some field like this. You could think of this as a fluctuation of the dilaton. Then this factor of e to the minus 2 phi will conspire with all these other factors, and it will produce for you a field in ADS. So it gives you it gives you the action of a free field in ADS. So in some sense, the massless modes, they follow the geodesics, quote unquote, in ADS. Of course, these are massless fields, but you could also talk about, for example, giant gravitons. And the giant gravitons actually follow geodesics in the ADS metric. So they neither follow the geodesics in Einstein frame nor in string frame.
I see. So that's how you make sense of that formula there. You put the massless modes in this ADS boundary.
Yes.
And then it's usual Witten diagrams in that ADS.
Yes. There's some small caveats, but for the 2-point function, that's correct. So one small caveat is, well, for example, even in the 2-point function, the formulas that you get have some z to some power. Okay, so they look like a standard formula for particle in ADS2, for example, massless field in ADS2, but there's some z to some power that is not accounted for. And so what you say is, well, if I change the dimension of ADS, then I can absorb those powers into the square root of the determinant. So that's why you need to choose a fractional dimension. So yeah, this is a little bit tangential to the main line of what we're going to cover, but this D here, okay, there are two separate facts. Two experimental facts. They turn out to be explained by the same thing, but let me just state the two experimental facts. First, in this metric, we have a black brane. It looks like ADS2 times S8, but the black brane has a factor 1 minus z to the d, where d is not 2, but instead some fractional dimension. So that looks funny. The second fact is what I just said. So if you take a massless field, you put it, you analyze this action, you will find some overall powers of z, and the overall power will be this 9/5, basically. So this 9/5 turns out to be the same factor here and here. So in both cases, you should think of it, the fields, as really living in some sort of fractional dimension ADS. Yeah, I could explain this further, but it's a little bit tangential to the main direction that I want to go in.
So I just wanted to comment on the earlier question. I mean, the definition of energy is associated with the choice of killing vector. It has nothing to do with the choice of frame. Going between Einstein frame and string frame is nothing but the theory definition, and conserved charge does not depend on the choice, what you call the elementary fields. And related to this, actually, the difference between Einstein frame and string frame is essential when you consider the massive string modes. And as far as I remember, I think the early papers actually made a mistake in solving the free wave equation in the Einstein frame rather than string frame as they should have.
Yes, yes. Yes, so when you solve the stringy modes in the massive stringy modes in string frame, you actually do not get a power law. You get some exponential decay. Well, yeah, indeed. So it's important to use string frame for those calculations. Yeah, so this is the Einstein frame formula. So in string frame, we should put some factors of the dilettante.
Repeat the question, please.
Yeah, what about the area? So I wrote this formula, which is entropy equals area, and that's area in Einstein frame. In string frame, I should put the factors of dilettante. Yeah, thanks. Okay, so one more comment. Since we bothered to explain this M-theory picture, which is this black string, right? You can think of this this solution, okay? You can think of this solution as being relevant for the very low temperature physics of the model, okay? So in particular, you can analyze the dilettante at the horizon, right? And the dilettante, if we're in the 't Hooft regime, the dilettante will be tiny, okay? But nothing stops us from taking an ultra low temperature limit where the temperature scales like some powers of n. In that case, the dilettante can grow, right? So the dilettante can continue to grow, and it can become so big that we should really, it becomes order 1, right? When it becomes order 1, we should really use the 11-dimensional description. As we go further down in temperatures, we will not just use the solution that we originally wrote down, which was the black string solution, but we will encounter the Gregory-Laflamme instability, and we should actually use the 11D localized black hole solution. So we should really think of it at very, very low temperatures as being more like an 11-dimensional Schwarzschild black hole as opposed to an 11-dimensional black string, okay? But if you're interested in observables which only probe the 't Hooft regime, it doesn't really matter whether you think that the extremely low temperature physics, which happens in this tiny region here, is a localized 11-dimensional solution or a uniform solution in the 11 dimensions. Yeah.
Is there a decoupling limit too in 11 dimensions?
Yes.
That would be different from the decoupling limit in the 10?
No. So okay. So this decoupling limit does not involve any factors of n. So it works whether n is small or large. And there's a further limit where we take n extremely large, and then we take the temperature to be like powers of 1 over n. So that's a further scaling limit, and that lands us into the 11-dimensional regime. But from the point of view of the decoupling logic, we could have done this at any temperature, at any value of n. So the decoupling argument works more generally, I think.
And we could have done it in 11 dimensions to begin with, or no?
So I would say that you always start with a 10-dimensional flat space region, and this 11-dimensional bubble grows deep into the infrared. Yeah.
Yeah, thanks.
Yeah, so the 11-dimensional region is related to the original BFSS conjecture, right? So here I've not approached it through the BFSS logic, I've approached it through this decoupling limit kind of argument. So yeah, the decoupling limit, it's for the D0 brane in particular, it was discussed in Idzaki, Maldacena, Sonnenschein, and Yankelowitz. So some paper from the 2000. Okay, one more thing. So one application of this black string solution is that we can evaluate one of the corrections that I just discussed, right? So in M theory, I think Shai already mentioned it in his talk, there's a famous correction, a famous protected correction, which is just r to the 4, right? It's some r to the 4 correction to the M theory action, and it's believed that in type 2a, the one loop r to the 4 term arises just from dimensional reduction of that one loop of that M theory r to the 4 term from 11 dimensions. Okay, so to evaluate that r to the 4 correction, we can just use the black brane solution and evaluate r to the 4 on the black brane solution. okay? And that produces us some coefficient here. So this coefficient B is known, and it's related to the M theory R to the 4 correction, the known M theory R to the 4 correction. Okay? What about this term here? So this came from this came from 8 derivatives, right? So this was a term like L Planck to the 6 R to the 4. There's also terms correcting this action, right? So this would be a term in this action, roughly, that looks like R to the 4, but has no powers of the dilaton. So it gives a 1 over n squared correction. In addition, we could have things like e to the minus 2 phi times R to the 4, which are suppressed by alpha prime cubed, right? Now, in order to accurately calculate this term, we would not just need to, we need to know the full nonlinear completion, right? So we need to know not just the R to the 4, but also arbitrary terms involving 8 derivatives, including terms that involve the Ramon field. And we do not know the full completion, okay? We don't know the full alpha prime cube correction involving Ramon fields. So because we don't know this, we don't know this term. This term C1 is unknown. The power here is predicted just from dimensional analysis. So just knowing that the correction is alpha prime cubed times R to the 4, you can get this power. But this particular number is not known. However, there's a Monte Carlo prediction for it. So, yes.
E to the minus 2 phi R to the 4 is a genus 0 term. You know it.
Yes, a tree level term. Yeah, so this
you know
term is known, but you need to know terms that involve the F as well. So in principle, this is just a tree level string theory calculation. But for example, you know, if there's, let's say, I don't know, F to the 8, you know, that would be a tree level calculation involving, you know, 8 external
But
guys.
if you just mean e to the minus 2 phi R to the 4, just the usual.
Yes, that term is known, but
term, yeah.
the full correction is needed to accurately evaluate the alpha prime cube.
The full super invariant, you mean?
Yes, the full super invariant, because
Okay.
this background has some non-trivial Ramon field and dilaton fields.
Okay.
Yeah, yeah. Yeah, so this is unknown. It's predicted, though, by Monte Carlo. So Monte Carlo actually did, the Monte Carlo group, in a series of increasingly precise calculations, they attempted to directly simulate this model by putting it on a lattice, right? So they put a Euclidean time lattice, and they do a Monte Carlo simulation of this model. And by taking a large n so they have to deal with the issues that we talked about yesterday, so they have to do a large n extrapolation. They also have to turn on a mass term to remove the metastability issue. And they have to do an extrapolation in both the mass term and the large n, and of course the continuum limit. So 3-parameter extrapolation in order to calculate the thermodynamics. But by assuming that the leading term has the correct form, and then putting in this exponent as well, and then just leaving one unknown, they claim that their data is good enough to actually give a prediction for the C1. Okay. Now, I would say that, well, we could discuss how much we should believe the simulation. I think they're fantastic simulations, extremely impressive. The most serious issue is the sign problem, though, in their calculation. So they simply put an absolute value in front of the determinant, and they do some small n experiments to argue that the sign problem is mild in this model. But I think it's fair to say that it's not clear what small parameter suppresses the sign problem. So it's not clear if it's suppressed by 1 over n or suppressed by low temperature or what. So I think you know, we don't have a systematic knowledge, systematic understanding of the sign problem that allows us to be confident that this calculation, even if you were to go to very large n and spend a lot of computational resources, whether this number calculated by Monte Carlo is completely reliable or not. Okay, so I think one goal of the Bootstrap should be to just compute this, this term, okay? So this, as we just emphasized, is just a tree-level term. It's the leading correction to the D0 black-brane solution coming from type 2A string theory. And it's slightly embarrassing that this tree-level question we don't yet have an answer to. So I think just calculating it from the Bootstrap, we could also compare it to the Monte Carlo result to see whether or not they're in agreement. And eventually, of course, we would like some theoretical understanding of this term. I mean, we like to compute it using string theory or some method. And I think that would be one target for, in the same spirit that Shai was talking about, doing a computation involving high precision and trying to learn something new. Okay. Yeah, it's 23/5. Yeah. Yeah, I think this power series
Can you
is in
maybe
t to the
repeat the
4.
question?
The question is, how close is the next exponent? I think the power series is in t to the 14/5. So, yeah.
So just a comment. Of course, the free energy at finite end is not. I mean, thermodynamics at finite end is not well defined.
Yes.
So I think probably the 1/n expansion is still well defined to order in perturbation theory, but e to minus n effects.
Yes.
Would be, well, at best imaginary, if it makes sense.
Yes, thanks. Yeah, so, yeah, she is saying that this black hole can evaporate, and it can evaporate. Okay, thankfully, this black hole looks a lot like an ADS black hole, and ADS black holes cannot evaporate. Okay, so if you put some massive particle, it will not evaporate in this black hole. It feels the ADS barrier. The exception is the d0 brane itself, right? So the d0 brane itself has a charge that's equal to its mass, and you know, it's obvious that in the zero temperature limit, the d0 brane is not repelled by anything, right? The gravitational potential is exactly canceled, and this means that this black hole can evaporate by d0 brane emission, okay? But d0 branes are heavy, so the evaporation timescale is very long, like e to the n.
Regarding Fernando's question, I think the next correction is due to d to the 4r to the 4, and that's 4 more derivatives. So that's going from the first to the second. It was 6 derivatives.
6 derivatives.
So this should be 2/3 times 14/5.
2/3 then.
Suppressed by that power.
Ah, yes, thank you. Thanks. Yes. Yes. Yes, thanks a lot. Okay.
Maybe it's a bit out of the direction you are going, but maybe we can discuss offline. But could you summarize a little bit more? What do we know? What else do we know about these correlation functions of massive and massless modes?
Yes. So in the supergravity approximation, we can calculate the massless correlators, the 2-point functions, 3-point functions, 4-point functions. The 3 and 4-point functions were actually only very recently done. Yeah, they look a bit like 3-point functions in a conformal field theory, but integrated over these extra dimensions. So it's not, they don't immediately look like the expressions that you'll recognize just by looking at them, but they're closely related to conformal invariant functions. That's for the massless modes. We also, okay, we can discuss, for example, giant gravitons. They also have some conformal behavior where delta is now of order n. That's another thing we can do. We can discuss massive stringy modes. Those we can analyze in some WKB approximation, and we get some non-conformal behavior. So we get some exponential decay with so it goes, those massive modes. So let's say a generic massive stringy operator will have a decay that goes e to the minus m times tau to some power. And you get this just from solving the geodesic equation in the string frame background. Yeah. Now you could ask, for example, these alpha prime cube corrections that I just discussed, they presumably modify these correlators. So they would modify the short distance correlators. So this is only true in the Tuft regime. Sorry, not just in the Tuft regime, but in the very low temperature regime, or the where tau is much bigger than 1 in Tuft units. Okay, if tau was of order 1 in Tuft units, you would also have to worry about these alpha prime cube corrections, etc. So these correlators would also get corrections, and I think if you could bootstrap them, it would be another way about learning about alpha prime cube corrections that would be independent, or slightly different at least from the thermodynamics. Yeah.
And you mentioned that the boundary, it's a region where we cannot trust, but we can still put operators there, because
yes.
if we put them at large enough separation, we believe that the part we cannot trust just depends locally on the operator, and I don't care.
Indeed, indeed. Yeah, so the idea is that, yeah, we put some correlators here. They propagate through this bad region. We don't exactly know, but most of the time they spend in the nice region where we can trust gravity. And that gives us this power law decay. At short times, if we put the correlators very close, then they only probe this sort of high curvature region. We don't really know the form of this correlator. Okay. Let me very, very briefly just mention one more thing, which is just to make contact with the BFSS conjecture. From the ADS-CFT logic, you could also consider a situation where, for example, you separate one of the D0 branes from the rest of the D0 brane clusters, right? And from the decoupling, well, let me just say that we can consider a probe D0 brane in this background. So this is just the dBi action of the probe D0 brane, and there are trajectories which look like this. So the probe D0 brane comes in from r equals infinity, it goes to some finite radius, and then it goes back out to r equals infinity. So this is related to scattering in this matrix model. So the idea is that you separate one of the eigenvalues of the matrices very far. It comes in, it then scatters off of the bound state wave function, and then it goes back out. Okay. Now from the dBi action, from the dBi action of a probe D0 brane, we can just write it down using that background. We get something like this. We get rho to the 7, 1 minus v squared over rho to the 7 minus 1. Okay. This minus 1 comes from the Ramon gauge field. Okay. And then expanding the square root, we get something like v squared. So this is the non-relativistic piece. And then something like v to the 4 over rho to the 7. And then also terms like v to the 6 over rho to the 14. Right, just expanding the square root. Sorry. There should be a rho to the 7 here. Yeah, so the only thing I wanted to say, just to make a very brief contact with the BFSS conjecture, is people in the past did a one-loop computation and matched these two terms from the matrix model side. So there's some precise coefficients here. They were calculated from the matrix model side, and they match what you expect from the dBi action. So that's one check of scattering, let's say, in this holographic setting. The interpretation of this was slightly different in the past. But okay, now let's go back to the Bootstrap in the remaining time. So this was all motivation for you to be excited about bootstrapping the BFSS or D0 brane matrix quantum mechanics. Okay.
Just one more. About these exponential decaying functions, were they measured with Monte Carlo as well?
I don't believe the exponentially decayings were measured. There was a check of one of these critical exponents in Monte Carlo.
Okay.
Exponential decay was claimed, but it was not very trustworthy.
Yeah.
Okay.
Yeah. Even this power law, well, yeah, I'll refer you to the plots and you can decide for yourself.
And is there so all these masses and deltas and so on, are they the eigenvalues of something?
Yes. So for example, this delta here, you basically just expand the spherical Laplacian on S8. And you consider some partial waves of, let's say, the dilitons or other supergravity fields, very similar to n equals 4. And this, Laplacian has various values. So for example, this delta, okay, so for this operator, so in n equals 4, we would just have delta equals k, right? In this context, we have a small modification of the formula. There's some 2/5 times k. And this should be interpreted as the quote-unquote fake radius of the ADS. So this is the, you can think of this as J, right? So J is some SO9 angular momentum. So Z is charged under SO9 now instead of SO6. And it carries some angular momentum. And if you like, this is some sort of BPS bound in the bulk theory. Okay. Yeah.
Is there an operator like the dilatation operator that I can diagonalize in the matrix model and get these M's and deltas?
Yeah, not that I know of, unfortunately. Yeah.
So about the exponential decay of the massive correlators, in fact, there was an attempt to even fit the mass, but not only the Monte Carlo data was extremely poor, but I believe that the exponents they're trying to fit was actually calculated wrong. As was mentioned earlier, I actually think there was a mistake of Einstein frame versus string frame. I think they just tried to fit the wrong number, and the data is so rough that you cannot tell with.
Okay, thanks a lot. Yeah, so let's now discuss bootstrapping BFSS. So spoiler, we're not going to calculate all these dimensions and masses and so forth using the bootstrap. Of course, that would be one of the eventual goals, would be to get many more things. We're just going to do the most modest thing that we could think of to just try to get started, okay? So again, we're going to try to just bootstrap simple one-point functions in the ground state of BFSS, the zero temperature one-point functions. The eventual goal is, of course, to combine all the ingredients that I'm mentioning to get more interesting physics. But we're going to start with what we can do, okay? So let me remind you of the ingredients in the bootstrap. Okay, so there was positivity, and there was some sort of equations of motion, right? In the ground state of the system, so BFSS is a supersymmetric quantum mechanics, right? It has n equals 16 supersymmetries. So in particular, we have a supercharge Q alpha, and we can write some expression for it. Maybe I write beta. So it looks a little bit like this. So this is roughly like the square root of the commutator squared interaction, right? And this is like, roughly speaking, the square root of the kinetic term, right, which is p squared. So this is the supercharge. This index beta, or alpha, runs from 1 to 16, so it's a spinor representation of SO9, okay? And we have 16 of them. And the idea is in the bootstrap, if we're just interested in the ground state, we can impose, instead of imposing the previous equation, which was the commutator of h with an operator 0, we can instead impose that the anti-commutator of Q alpha with some operator O alpha is 0. So in the ground state is supersymmetric, we can impose this equation, right? So that's one change, let's say minor change. The other thing we want to impose is SO9 symmetry.
Alpha in the operator is a typo, right?
Alpha in the operator.
Why is there an alpha in the operator?
Yeah, okay, so let me explain that. So because we impose so the ground state is SO9 invariant, so any correlator that has that is not an SO9 singlet will immediately be 0.
Okay,
so in order to get a singlet, we need O to be an, yeah. So that's also why I wrote an anti-commutator. It's also true that the commutator of any supercharge with an operator vanishes in the ground state, but it's not a useful equation because in order for SO9 symmetry, we need there to be an alpha index. That means O is fermionic, and therefore we should use the anti-commutator. Okay, very good. So this is basically the main thing that we're going to impose besides positivity. So you see what the strategy might be. The strategy would be to simply enumerate all possible operators, O alpha, right? And then derive these equations and try to plug them in into some giant matrix, some giant positivity matrix, and check all the positivity requirements, similar to what we discussed yesterday. Okay, but there are several technical details that we need to do in order to make this practical. So let me illustrate one of them. Well, let me start with something very easy. So you might need a scheme. So obviously we're not going to be able to enumerate all possible operators, right? We need some scheme to decide what operators we're going to keep up to some cutoff. And the scheme that we chose was the following. So we defined some level of an operator. So the level of the operator is defined as follow. So the level of a x is 1. The level of a p is 2. And the level of a fermion psi is 3/2. Okay, why did we choose this scheme? Well, it has the nice feature, okay, that if you act with the Hamiltonian, so if you take the commutator of the Hamiltonian with any operator, it increases the level by 1, right? So for example, the commutator of x with the Hamiltonian is p, that has level 2, which is 1 higher than this, right? Even better, if you take the supercharge commutator or anti-commutator with an operator, it increases the level by 1/2, right? So the superpartner of X is psi, and indeed the level has 3/2 compared to 1. Okay? So this is some natural scheme, and the idea is that we assign a level to a composite operator that's just the sum of the levels, right? And we go up to some maximum level, okay? So in our paper, we went up to level 9. Okay, so we consider all operators which have, let's say, up to 9 x's, but they could have also fewer numbers of p's and psi's. Okay? So that's one easy thing to deal with. The thing that is sort of non-trivial to deal with, the most non-trivial thing to deal with is actually the SO9 symmetry. So from what I said so far, it sounds a little bit trivial. It sounds like we just need to work with SO9 singlets, okay? But it's not totally trivial because of the following reason. Okay, so to illustrate this, just consider the positivity of this quantity. So trace xi, xi, right? Obviously, this quantity is positive in the ground state, right? But how do you know this? So you know this because you view this as the square of the operator xi, right? So trace xi, xi is a singlet, of course. But in order to know that it's positive, we have to reference a non-singlet. Okay? So this means, let's try to do an example that's a little bit less trivial. Okay? So let's now consider this object, m alpha beta eta epsilon. Okay, this is a 4 fermion correlator. Okay, we think of dividing it into 2 pieces, right? So we think of this as the ket and this as the bra, and therefore this matrix should be positive in the sense that if we view this as one of the matrix indices and alpha beta as the other matrix index, it should be positive, right? Okay, let's think about that matrix now. So let's think about this matrix. So this is a positivity matrix that involves 16 to the 4 components. That's a lot of components. I mean, we could actually deal with the matrix of this size, but for more general operators, you see it quickly gets out of hand, right? So we don't want to literally write down all components of this giant matrix and impose positivity, right? What we want to do is use group theory, right? So the idea is this matrix, using SO9 symmetry, SO9 invariance of the ground state, we can write down what possible structures could appear, right? So one possible structure that could appear is just delta alpha beta, delta eta epsilon, right? With some unknown coefficient A0. We could also have something like A1, delta alpha beta, gamma I, alpha beta, gamma I, eta epsilon, right? So the fact that these 2 indices are the same is related to SO9 symmetry. We could have all the gamma symbols up to gamma I, j, k, l, right? So there'd be some A4 here, alpha beta, eta epsilon. Okay? And this is the most general SO9 invariant ansatz for this matrix. Okay, so we see that originally we had many components of this matrix, but really it's parameterized by just 5 unknowns. Okay, and if we like, we can draw a little picture. Right? So here's the trace. Here's alpha, beta, eta, epsilon. And what we're doing is we're doing some block decomposition, right? So alpha and beta can fuse to be the identity, so the identity representation. Or it could fuse to be, so this could be the identity. It could also be the vector representation, which we could call 9. It could be some antisymmetric tensor, all the way up to an antisymmetric tensor of rank 4. So most generally, we should put here some representation R, right? Okay, so that's, so far, we've just drawn a picture. Now let's try to make the picture a little bit more useful. So for this, we need to consider one of the other ingredients that I talked about yesterday, which was cyclicity of the trace, right? So cyclicity of the trace gives you something non-trivial in general, right? So in particular, let's try to move this fermion psi alpha through these 3 guys and put it on the right-hand side, right? So if we do that, we'll have trace psi beta, psi eta, psi epsilon, psi alpha, but with a minus sign. The minus sign is because we anti-commuted 3 fermions through, right? There's also a correction. The correction comes from the fact that we have to take into account the non-trivial anticommutators, right? So there could be an anticommutator from alpha and beta that gives us a 1/2 delta alpha beta, and then we'd have a trace of psi eta psi epsilon. Trace of psi eta psi epsilon on kinematic rounds is always just delta eta epsilon. That was just one of the commutators. There's another one, which is when you commute this guy through, it could, for example, pick up a commutator with this guy, right? So that would give you another 1/2 alpha epsilon delta beta eta. Okay, now let's look at this trace. So this trace, we could again do the same decomposition as before, right? So now we do a decomposition beta eta epsilon alpha. That's basically just the same diagram but rotated, right? So if you rotate the diagram, you get this. So
Sorry, I don't understand this. I think I missed something basic. I thought traces, I just rotate, and that's it. Why do I get these extra terms?
yes, yeah. So traces, you just rotate. So, okay, you have to remember that there's two things going on. This is a trace of not just matrices, but each element of the matrix is an operator. So when you commute, so this trace is a matrix trace, but the elements of the matrices are operators. So you pick up something non-trivial when you go through.
Okay.
Trying to understand what to expect. So these expectation values, so these are operators. This is a regime in which these scaling dimensions, weird scaling dimensions appear.
In principle, yes, yes.
So the expectation values must be some numbers times the 't Hooft coupling to the appropriate power that's given by that scaling dimension.
Okay, so I haven't discussed specifically what I'm computing. If I'm computing, let's say, a generic operator, it will be some mixture of massless modes and massive stringy modes. The only thing that this kind of argument tells you is that in the 't Hooft regime, you expect to get an order 1 number times the 't Hooft coupling. We can't really say further
But
what
't Hooft coupling to what power?
power determined by dimensional analysis, essentially. So like, for example, if we consider trace xi,
Yeah.
x has some dimensions, we use g squared n to make it dimensionless. We multiply it by some powers of g squared n to make it dimensionless, and then
So
it's
the
order 1.
the engineering dimensions.
The engineering dimensions, yes. Yes.
And how is this then related to those?
At this
Scalings
level,
over-
it's not related. So in order to discuss that, we would have to discuss some 2-point function, for example. Yeah. So just the 1-point function itself is not clearly related to any of these dimensions.
Okay, thanks.
Yeah. Okay. We could discuss this a little bit more. So if we considered a massless mode, so if we considered like there's some particular SO9 singlet which is also a massless mode. Okay. We could consider that 1-point function. In the ground state, it would just be 0. But its temperature dependence would be determined by the scaling dimension. So the 1-point function of that special operator would be like temperature to some delta, which is given by the supergravity delta. So that would be something we could hope to test. Yeah. Okay. Yeah.
Sorry, and those 1-point functions, what's the cartoon that I draw? For 2-point functions, I understand that they propagate a long time in the good geometry.
Yes.
How do I think of the 1-point functions?
Yeah, I think one cartoon that I have in mind is that there are some, okay. So for example, this stringy 1-point function that I just discussed, it could get corrections, for example, from the r to the 4 terms, right? So there could be some interaction between the massless field and some higher curvature term. The higher curvature term is large in this region here. So normally, like, for example, in ADS black holes, we draw a 1-point function, and we say, for example, that the 1-point function gets a contribution from the singularity, right? Because that's where the curvatures are very large. So like in this paper by Malasena and I'm blanking for some reason, but this 1-point function can be interpreted as coming from some contribution that is sort of behind the horizon and very significant because the higher curvature term gets very big near the singularity. But in this geometry, there's also a high curvature region just near the boundary. So I think the moral picture that we have in mind is that the one-point function is sort of contaminated by this near this sort of UV region. This is related to why I say it's not totally clear how to actually get a holographic prediction for these one-point functions. So in principle, in this high curvature region, in principle, you should worry about operator mixing and all sorts of stuff. And we don't really know how to cleanly separate it. So from this big point of view, I think this one-point function is some sort of, it gets a contribution from an energy scale that's of order 1 in Tuft units, and that's not where we have a reliable gravity picture.
So just to understand, I mean, usually, of course, in the CFD context, we say the one-point function just means you have some mixing with identity operator. But you're saying that here is more than that because you can consider spectral decomposition at level of the two-point function, and so the one-point function doesn't just necessarily reflect the mixing with identity.
Yeah, I would say that the analogy that I have in mind is that in the CFT we consider the CFT at finite temperature. Then the one-point functions can be non-trivial, right? So there's some non-trivial coefficient c times t to the delta. And that's, well.
But you're saying here, even at 0 temperature, you can have some non-trivial one-point function because of singularity? Is that the, because without that, if it weren't for that singularity, there is no bulk, kind of by definition, the one-point function would be 0.
Yes, by definition it would be 0. Well, this is a cartoon because I don't know how to, disentangle the operator mixing and so forth. But I think the bulk picture does suggest that you have one-point functions which are of order the Tuft scale.
But I'm just trying to say that the way that one would disentangle the operator mixing is to a two-point function.
Yes.
And what you're saying is that even after you have disentangled operator mixing at level two-point function, you can still find non-trivial one-point function.
Yes, I agree with that statement. Yeah, I agree. You can use the temperature dependence to make a non-trivial.
Would you agree that normally we do the disentanglement of the two-point function in the UV region, right? To define good operators, but here we cannot do it, right? Normally in a theory we renormalize the operators by diagonalizing the two-point function in the UV region. So it will be the similar problem here.
Let's say if you consider just a weak string coupling limit, right? I mean, I would think that you can still talk about, by looking at the spectral decomposition two-point function, you can say unambiguously what are the single trace operators due to particular massive string states. And you would already have resolved that operator mixing by looking at two-point function.
Yeah, I think in principle, if you could solve string theory in this curved background, you could do that.
But it sounds like you're suggesting that because of singularity, somehow, even after that, you can still have the non-trivial one-point function. Right?
Yeah, I think you get a one-point function from some coupling between delta phi squared, perhaps, and some higher curvature terms. And those usually we don't, in, let's say in vacuum ADS, that higher curvature term does nothing. In a black hole background, it's very tiny except near the singularity. But in this background, there's something different, right, which is the higher curvature term gets big near the boundary. Yeah.
So the structure of this holographic view as well as the Hilbert space is very similar to n equals 4 supermills on the 3 torus, just with supersonic boundary condition. I mean, but there, of course, we have some kind of preferred basis of single trace operators. Would you say the same thing about the one-point function there?
Well, but there's nothing bad about the UV region, right?
Not about the UV region, but the singularity has to do with the infrared, right? It's about somehow has to do with the ground states, and also for n equals 4 supermills on T3, the ground state is also funny because that's also not gapped.
Well, I don't have something immediate to say. Yeah. I do think, well, I would say another cartoon is that there's an RG flow here, right? So that's somehow important in this discussion, I think. Okay. Let me try to finish explaining this diagram. So, okay. So the point of me drawing this picture was to tell you that this cyclicity of the trace is effectively a crossing relation, right? So in particular, we did the SO9 decomposition in this channel in the first line. And because we want to impose cyclicity of the trace, we're forced to do it in a different channel. So these 5 coefficients, A0 up to A4, we need to solve some linear equations in order, this cyclicity of the trace enforces some linear relations on A0 through A4, right? So what is that linear equation? So we basically have AI times this diagram, right? It's equal to AI times this diagram plus some additional contractions. So this delta alpha beta can again be represented by some diagram like this. And this delta alpha epsilon should be represented by a diagram like this, where this is 1. Right? So here we have some Ri. Right? And we should think of these as vectors. Right? Now to solve this equation, we can take the inner product of these blocks. Right? So in particular, we can take the inner product, let's say, with a block like this, Rj. Right? So the inner product between this and this is basically just delta Ri, Rj, up to some number. On the other hand, this inner product is non-trivial, right? This inner product is nothing but the 6j symbol, right? It's the crossing kernel. Right, so if you rearrange these lines, so these lines get contracted, then you rearrange them, they become like this, right? And if you have some Ri here and Rj here, right, this dotted line on the back side is the Rj, and the one on the front side is the Ri. Right? So this is some matrix. So this is a very concrete matrix which is labeled by representations, Ri and Rj, and it's given by the 6j symbol. And if you calculate the 6j symbol, you will then get some sort of linear equation, some matrix equation for these AIs that you can then solve. Okay? So this is just the linear equation in 5 variables, but it illustrates the sort of general strategy that you'll have to do. Okay? So you have some linear equation in 5 variables, you solve it, and then you get you reduce those 5 variables to basically just 2 variables. Okay? So those 2 variables can be parameterized in terms of, let's say, A0 and A1. So you still have A0, A1, but then you have A2, A3, A4 that are functions of A0 and A1. Okay? And the thing that you learn is that all of these coefficients are positive, right? So in this kind of OPE decomposition, right, the A's you should think of as the squares of the OPE coefficients, right? So they're positive. So all the AIs are basically positive. That's what positivity of this matrix implies. And this gives a constraint on the 2 A0s and A1s. Okay? So what I'm trying to explain is how you would get a constraint, for example, on the correlator psi alpha beta, psi eta epsilon, gamma I, gamma I. Right? So this is some correlator that's now a singlet, right? So all the indices are contracted. It's a singlet, and its positivity is determined by doing this sort of somewhat elaborate game. Okay? The positivity, yeah, it's very similar. Okay, part of the reason why I explain this to you is because it's very similar in spirit to the conformal block decomposition, of course. There you have the positivity of the OPE coefficients. Here we have some positivity of some SO9 coefficients. Okay, so at the end of the day, we only work with SO9 invariance, which is equivalent to just working with all these AIs. And we work through all the group theory to both get positivity constraints and to determine these crossing relations which have to be solved. Okay, so by doing all of that, we're able to make some plots. So I think I'm almost out of time, or I have 0 minutes. Okay, maybe next time we'll discuss the plots that you get from doing this procedure. All right, thanks a lot.
So this group theory, this SO9 group theory that you have to do, is there something that can be computerized?
Yes, yes. Well, this is a painful question. So yeah, we're still trying to computerize it. I mean, in principle, it's just, well, what do you need to computerize? Computation of these crossing kernels, the computation of the OPE coefficients. And none of these are like very difficult things, but it's a little bit messy, and yeah, we're still in the process of fully doing it. Yeah, I've also glossed over some other details. So like in the equations of motion, the group theory also comes back. when you compute this commutator, yeah, let me not try to explain it right now. But basically, when you use this equation of motion, when you do one decomposition, you can generate another decomposition. So then you have to relate the two different decompositions, again, using some crossing kernel.
Yeah, just a minor comment. Actually, in the last part, yeah, the AIs, due to some reason, some of them, they are not really positive, but negative.
Yes.
So due to the parity of the gamma,
Yes.
you can think of it this way.
All right. Let's thank Henry again.